More than 10 years ago, when I was an undergraduate, I thought that many worlds was obviously the correct interpretation. And I was genuinely puzzled as to why other people didn't find it completely convincing. My confidence in many worlds was based on the following two postulates, which I personally found pretty compelling. Number one, hidden variables do not exist. And two, quantum dynamics is linear. Let me take a moment to explain why I like these postulates. Firstly, despite great efforts, no experimental procedure has ever succeeded in finding additional variables that would render the theory deterministic. When the theory tells you that something should exist, but you just can't seem to detect it experimentally, history shows that a good rule of thumb is to try postulating that it's not there. Think of absolute motion, for example. Secondly, the dynamical equations of quantum mechanics seem to be linear, meaning that if you take a quantum superposition of any two solutions to the equations, you get another solution. This is actually kind of unusual in physics, where most familiar kinds of dynamics, think fluid mechanics or gravity, are described by nonlinear equations of motion. When some unexpected or peculiar feature of your theory is supported again and again by experiments, history shows that's a good candidate for elevating it to a postulate. The funny thing is, all these years later, I still stand by both of these postulates. But back in those days, I also believed in a third postulate, namely, quantum states describe states of reality. It turns out that if you want to have postulates 1, 2, and 3, it's very hard to escape the conclusion of many worlds. So what's wrong with that argument? Well, nothing really if all you want to do is explain the existing theory. And as an undergrad, that's all I really cared about. So many worlds seemed perfectly good to me. But as I progressed in my physics career, I became more concerned with the problem of going beyond quantum theory. For instance, trying to extend the theory to include gravity. And when you're in the business of theory building, it's not good enough to stop at an interpretation. You have to then use the interpretation to guide you in building new theories. And this places a whole new set of demands on the interpretation. Not only must it explain what has come before, it must also provide strong constraints on what else might be possible. Looking again at those three postulates, it's kind of obvious that the first two are extremely powerful because they place strong restrictions on the possible theories. By contrast, the third postulate is notable for not being based on any experimental observations. It just expresses a philosophical standpoint, and its only purpose in the system seems to be that it leads us to many worlds. So is many worlds good for something? A basic test of the strength of any principle is to take it as a postulate on its own and see what it implies. For example, if we postulate that some theory must have many worlds, does this requirement also force us to conclude that the theory's dynamics must be linear, or that there cannot be variables that predetermine measurement outcomes? No, it turns out it does not imply either of those things. So as a postulate on its own, it actually doesn't have much power at all to constrain the possible theories. Here's another test. Does assuming many worlds make the other postulates at least seem natural? In the case of linearity, the answer is definitely not. A priori, if many worlds existed, we should expect to be able to visit them or at least observe them directly. The only thing that actually prevents us from doing so is the linearity of quantum dynamics. In light of many worlds, the linearity postulate looks kind of conspiratorial. If the worlds are really there, why should nature conspire to hide them from us? They seem no better than hidden variables as far as I can see. All of the heavy lifting of constraining the set of possible theories is really done by the postulates of linearity and no hidden variables. Many worlds provides no additional help and in fact just seems to get in the way. Remember, there's no experimental basis for that postulate 3, which is what leads to many worlds. It's a purely metaphysical assumption. Why cling to it? Maybe there's some other postulate 3' that we could put in its place, such that the combination of 1, 2, and 3' leads to a new interpretation which does have the power to restrict possible theories beyond quantum mechanics. Shouldn't we investigate that possibility? If our goal is to build theories beyond quantum theory, then many worlds is useless at best. And at worst, we could describe it using Einstein's words, which ironically he used to describe the Copenhagen interpretation. It's a tranquilizing philosophy, a gentle pillow for the true believer from which they cannot easily be aroused. So let them lie there.